Alright, in this video I'm going to be talking about the definition of a limit and, some examples of graphs. Really, we're going to be looking at this graphically. We're going to be looking at graphs of functions where limits exist and where they don't exist. So I'm going to just kind of jump right into it and show you some discontinuous graphs, because these are going to be the ones that are most interesting for us to talk about when we're talking about limits. Alright, now I'm actually going to show you a couple of cases of graphs of discontinuous functions before I give you the definition of a limit. And then we're going to come back and look at these, through that lens. So the first is the removable discontinuity. And I am assuming that you've seen some discussion of discontinuity in a previous class and some kind of discussion of limits. I am assuming that in your pre-calculus. If you're not familiar, I don't think that's a big deal. I still think you'll be able to follow along with this. But a removable discontinuity is what we would consider a hole, right? So what I'm going to do is I'm going to draw the graph of a function, and we're actually going to be able to write down the equation for this function. And I think what I'm going to do is I'm going to draw it like this. Okay, so you think... Nope, okay, I need to go one higher. Alright, so we've got ourselves a nice line with a hole in it. And it appears that this hole is at the place where x equals 1. Okay, and then, if we're to believe that the y scale is also 1 per square, then this looks like this is the graph of y equals x plus 2, but with a hole at x equals 1. And just remember, okay, so if I'm going to call this f of x, we can actually write an equation for f of x using what we know from pre-calc. Okay, we know that if it looks like x plus 2 with a hole, then what it is it's really x plus 2 multiplied by some factor that's the same on top and bottom. Because remember, those holes come from 0 over 0, or come from when you factor a rational function on top and bottom and they're cancelable factors. That's where we're going to see a hole come from. So if we're seeing the hole coming at x equals 1, I'm going to say that that's going to be x minus 1, and this will also be x minus 1. I'm just reminding you of something that you already know from pre-calc. Okay? Now, f of 1, if I tried to plug in 1 into the formula I have for f, I'd get 3 times 0 divided by 0. Well, that's 0 divided by 0, and what they probably told you in your pre-calculus class is that 0 over 0 is not equal to 1, it's not equal to 0, it's not equal to any real number, it's undefined, right? We cannot divide by 0, it's not an option. So I'm going to say that f of 1 doesn't exist. Okay, from here on out, I'm going to abbreviate that with D and E, because that's an acceptable abbreviation in this course. And if you look over here on the graph, that's why we see that hole, right? Is because any other time, this fraction is just equivalent to 1, right? Whatever we're multiplying by x plus 2. Okay, so it's just the same as x plus 2, unless it's here where it's 0 over 0, because it's not the same. Okay, but what we can say, well, because f of 1 is pretty much like us looking at just this, right? We're only seeing that there's a hole there, that there's no graph of a function there. Okay, that's all we can see. But if we consider what's happening nearby, we can see that the graph of the function is clearly approaching 3, right? And then it pauses and then moves on. So we can say that the limit of the function, the limit of f of x, as x goes towards 1, is going to be equal to 3. Because the closer we get to x equals 1 from both sides, the closer y gets to 3, the closer f gets to 3. So that's why the limit of f is 3 as x approaches 1. Okay, I still haven't told you what really the definition of a limit is, so I'm just kind of giving you the intuitive picture. Okay, and then I just want to point out that, this f of x here, this is the argument of the limit in the same way that, 2 pi over 3 could be the argument of sine. Okay, the limit is something we take of something. So I think that's about all I have to say about this case. All right, next I'm going to talk about a jump discontinuity. Okay, so I'm going to just draw another graph of some function. I'll probably call this one g. Okay. And I'm going to say that this is going to have a discontinuity maybe at x equals 2. So what I'm going to do is I'm going to say maybe g approaches from above, and maybe it's a piecewise defined function. You might remember those from a previous course. And maybe it goes all the way up to 2, and then it starts following a new rule. Like maybe over here it starts up here, and then it goes on like it's increasing, and then all of a sudden it decreases. It has a change of heart. Okay, something like that. This is a discontinuous function. This is a jump discontinuity here, okay, where we have a full break in the graph. Okay, and then I'll be able to tell you more about the jump discontinuity in terms of limits once I actually define a limit. Okay, now I do need to point out if this is g of x, start with the discussion, what is g of 2 equal to? Okay, well, remember g of 2 is where we see the graph of g up above x equals 2, and this, when the filled in circle, is where we see the graph of g. Okay, so this is 1. Now, if I go and try to, follow with my fingers to talk about the limit of g as we approach, well, it's really doing two different things, right? Because of the nature of the graph, it's broken. So I don't know if it's doing one particular thing, but what I can for sure say is that this right piece is approaching g of x equaling 3, and the left piece is approaching g of x equaling 1. Now, the interesting thing is that over here, g does actually equal 1, but over here, g does not ever actually equal 3. Okay, over here, it's going to equal 3, but over here, it never actually does. Okay, it appears that we can get as close as we want to 3, like 3.01, we can get there. We could get to 3.001, and really, if you name any number that's above 3 and really close to it, we could get that close by of x sufficiently close to 2 on this side. And that's actually what the definition of a one-sided limit is. Okay, but I'm not going to quantify that because I don't want to get bogged down in epsilons and deltas in this video or in this course, really. If you're going to be in my class next year, we can jump into that. If you're just really curious about the formal definition of a limit, I can talk to you about it, but I'm not going to go into it in this video. So, what we're going to say is that the limit as x approaches 2 from the left side, well, left is not a particularly mathematical description. Okay, what would be better is if we said from the negative side, the limit of g of x is equal to 1. We're approaching 1, and we do actually hit 1. Okay, now we can also say that the limit as x approaches 2 from the right. Again, right's probably not the best thing. It would probably be more appropriate to say from the positive side. And that limit is going to be equal to 1, 2, 3, 4. So I think I said it was 3 earlier. I just miscounted squares. Okay. Okay. And I'm not really sure what we should say about the limit as x approaches 2. There's not like one specific behavior. I mean, maybe should we lean towards this one or that one? Or, well, you don't know because you don't know the actual definition of the limit. Okay, so I think I'm going to give you that now. Okay, and what we're going to say as our definition of a limit is that we will say that the limit equals L if the limit as x approaches c from one side is equal to the limit from the other side. And they both equal L. Okay, so the value that they would agree on would be the value of the limit. Okay, now if these two things are not equal, then we will say that the limit does not exist, and we can say D and E. Pretty soon here I'm going to show you some reasons for limit non-existence, and I'm going to want you to use them. Okay, I'm going to want you to explain to me why a limit fails to exist. when it doesn't exist. So, okay, I'm going to jump back to the previous example. Okay, say over here, the jump discontinuity, I didn't leave enough space, I should have, but maybe I'll write over here that the limit as x approaches 2 of g of x fails to exist, say d&e. That's kind of over on the edge of the page. All right. Now, I think I'm going to, and then over here, pardon me, I was going to go back over here to where we did say that the limit equals 3, okay, just because I kind of said it did. But from the left side, I'm approaching y equals 3. From the right side, I'm also approaching y equals 3. Okay, those one-sided limits both equal, and they agree, so that the limit is 3. Okay, even if f of 1 is not 3. Okay. Now, if f of 1 was 3, if this was a continuous function, well, then the value of the limit would be the value of the function, right? Because it's approaching here, it is here, it continues to go there. That's really what it means to be continuous. But I'll talk to you about that, I think, 2 times from now. All right, next I'm going to tell you about reasons for limit non-existence. I'm going to kind of draw you a picture of each of them. There's going to be 3 of them. I'm going to actually scroll it down so I don't have part of the definition of limit in this picture. All right. All right, whoops. Okay, so first we could have disagreement in one-sided limits. Right? We already saw that. Disagreement in one-side limits. Okay. And that's basically what we've seen is a jump discontinuity, right? That is the hallmark of a jump discontinuity, is that we've got 2 different pieces and they are not meeting up with each other. So that's really what we have, is disagreement in one-sided limits. So, maybe something like and maybe I'll even spice it up and put the actual value of the function right here. Okay, something like that. That's going to be a disagreement in one-sided limits. Because over here, I'm going to something larger than what I'm going to from the right. Second, we could have an infinite discontinuity, unbounded behavior, basically a vertical asymptote. I think that's what I'm just going to write it as vertical asymptote. No, because I could say that we're going to consider limits as x goes to infinity, and as x gets bigger and bigger, x squared also gets bigger and bigger. And it's not a vertical asymptote situation. It's just that, if you take a huge number and you square it, it gets even bigger, and there's no upper limit to that. So I'm going to say unbounded behavior. And that's just going to look like, it's going to be related to infinity. So I'm just going to maybe draw a picture of a vertical asymptote and say, okay, up here, maybe it's one of those types of vertical asymptotes that they hug up against, like 1 over x squared. Okay. And because they're not approaching any one real value, it's just getting bigger and bigger the closer we get to this x value from both sides. You're going to see next time we can say that that limit goes to infinity. But infinity is not a real number, so we can't say it, equals some real number, and then by default we say that limit doesn't exist. Okay. And then lastly, I'm going to show you the third one is going to be limit doesn't exist due to oscillation. And this is not going to actually ever happen in this class, but I do need to make you aware of it. Basically, two of the easiest to understand ones are the limit of equals sine x as x goes to infinity. And you don't really know what that is yet, but just envision y equals sine x. It just keeps going up and down forever, and it doesn't just get closer to one thing as x gets bigger and bigger. So there's no limit to that because it goes back and forth between -1 and 1. But the classic example is y equals sine of 1 over x. Or cosine of 1 over x. They look pretty similar. And I'm going to grab a graphing calculator. The only graphing calculator I've got in my house is a TI-83. And so I doubt it's going to be super great on camera, but it's the best I've got right now. So sine of 1 over x. And I am only going to show you kind of the right side of it, just to kind of give you or maybe I'll show you the negative side so you can see it get traced out. No, I think it'll trace out the right side first. Yeah, so I'm going to go from x being 0 to 4, y being 0 to 4. No, I need that to be like, how about -2 to 2? And yeah, that'll be good. I've got sine of 1 over x here, and let's graph this thing. Okay, that didn't provide me as good of a picture as I had hoped, but that's going to be all right. Okay, what we're going to do is we're going to zoom in. I'm going to clear off the screen a little bit. Let's get some dust on it. I'm going to zoom. I'm a little concerned because let's see. I'm selected zoom in, but I'm going to zoom in around x equals 0. That didn't go well. Okay, but you can kind of see that it's packing in more waves. And that's really what's happening, because as x gets bigger or closer and closer to 0, I'm dividing by a number closer to 0, which is causing the argument of sine to get bigger and bigger. And as sine gets bigger and bigger, it just packs in more waves. So let's actually change the window here. Let's change the y max to 1, -1. Let's change that from -0.1 to 0.1 instead, and see how many. That's a much more accurate picture of what's going on. And if you're interested in this function and you want to talk to me about it more, you can just do that at your own leisure. But I think, in the interest of time, I'm going to stop talking about wiggliness, because it's just not going to come back up again in this course. Okay, but these are the three reasons for limit non-existence. All right, and the last thing I need to tell you about, because it is a little bit relevant on the homework, is the linearity of limits. It's kind of a property of limits. And I think that you would probably come to this conclusion on your own, without me telling you this, but I am going to be explicit right here about it. So I'm going to, maybe I'll just do it like the homework and change the numbers up a little bit. I'm going to say, suppose we have a function h of x. And a function g of x. Okay, I'm going to say that the limit as x approaches c of g of x and the limit as x approaches c. I'm realizing I might be off the screen. I don't have the video up on my computer. Yeah. And the limit as x approaches c of h of x both exist. then like if a is some constant, the limit as x approaches c of a times f of x is equal to a times the limit of f of x. You might be like, well, why would I need this? And I'll show you the example problems. Oh, whoops, I forgot there is no f. It's g and h. So we can factor out a constant. So if you know a limit and they ask you about some kind of related limit, you can usually find it out. Okay, and also the sum of the limits is going to be the limit of the sums, provided that they both exist. This will be true. The limit of the sum is the sum of the limits, provided that they both exist. Now, with a equals -1, that could give you subtraction or any constant multiples of any of these, or linear combinations really is what I would call them. Okay. Now, for example, what is this even? It's like, suppose you're given a couple functions. Because I have seen this before, these types of items. Suppose, limit as x approached 1, or no, that was what it is in the homework, about 9. The limit as x approaches 9 of a of x is equal to -2, and the limit of b of x as x approached 9 is equal to 7. Okay, oops, I need to scroll this down. Everything else is zoom out. Okay, yeah, that'll do. Oops. Let's see my tablecloth. All right. They might ask you to find the value of the limit as x approached 9 of, 3a minus 2b of x. I just made those numbers up. Okay, and well, that would be 3 times the limit of a minus 2 times the limit of b, because of the linearity of limits. Okay, so really what this is going to be is 3 times -2, right, minus 2 times b is going to 7. Okay, and that's a safe place for us to stop. We don't actually have to do the arithmetic in this course, and I'll explain that to you more at a later time. But this, if you want to stop here and leave this as your answer, this is numerically equivalent to the correct answer, which means that it is good enough for this class. So I've got -6 minus 14 equaling -20, but this is not a necessary step right here. And if you're prone to arithmetic errors, I'm going to encourage you to stop at a place like that. But you'll get more comfortable with that as time goes on. And that's all I've got for you in this video.